Just going to run through the test review problems and do some solutions and comments. So number 1, we've got f of x equals 2 to the minus x plus 1. And we want to graph that. And one thing that's really important is the asymptote. Remember, that's really an important feature of the function. We discussed that in one example with like a 1 like 15 times 1 minus e to the something. And you want to really pay attention to that. So, well, I'm going to cheat a little bit and have the computer do it and then just discuss how you would do it by hand. Well, this is not at the most plausible scale you would use by hand, so let's just real quick change it a little bit. Maybe from minus 2 to 2. Okay. Alright, so what's going on here? 2 to the minus x plus 1. So it's the 2 to the x graph. And in fact, let's go ahead and graph that as well. Okay, and you need to be able to do that definitely from scratch. That goes through 0, 1, as all basic exponentials do. Goes through 1, comma 2. Asymptote on the x-axis and then swooping up and to the right. Well, what have we done? We've switched it left and right with the minus attached to the x variable, and then we shifted it. And it's a little tricky when you have a flip and a shift. It's even trickier than usual to figure out exactly how it's shifted. And so you just want to plug in a couple points. You know it's flipped and shifted, so it's going to be something swooping down, and it's shifted one way or the other. Just plot a couple of points. Put in 0. You get 2 to the 1 is 2. Plug in 1. The things in here cancel. You get 2 to the 0 is equal to 1. Okay, now we know that in fact this point got flipped and then shifted to the right, which is a little counterintuitive from our usual thing. But again, flips and shifts together are hard. But just plot a couple points. Now, on a calculator active test, I wouldn't ask you a question exactly like this. It might be like a matching question, or here's the graph, find the function. But again, the key thing is to look for explicit points and figure out what graph would produce those explicit points, and then also have a sense of, is it shifted, is it flipped, stuff like that. Okay, so 5 it's another graphing problem with a logarithm. That's log base 3 of x minus 1. Again, this has an asymptote. Now this has a vertical asymptote, and that's going to be important. I'd like you to graph that explicitly if I asked you to graph something like this, or if I give you a graph, you want to really look for that asymptote. Here, this is really a basic example because it's just a basic log graph and it's just shifted to the right by 1. And so you just have to be able to graph or recognize, if it's something where I give you the graph, the basic graph, and then shift it around a little bit. So let me change the x's a little bit. Let's say we go from minus 1 to 10. Okay, so now notice I asked it for minus 1. Minus 1. That's interesting. It's not giving me that. Let me actually explicitly make it go x is minus 1, because it's actually being smart enough. It's saying, you know, there's nothing out there. Why are you asking me to plot that? Because when you take the log graph, let me give you log base 3, unshifted. When you plot that, how do you do that? It's got an asymptote along the y-axis. They always go through 1, 0. And then the simplest point to plot after that is log base 3 of 3 is equal to 1. So 3 comma 1. If you want one more point to plot, find the next power of 3. Log base 3 of 9 is 2. So there's that graph, and we're just shifting it to the right by 1. So in particular, it doesn't have this in here, but what I would really like from the computer here would be put in a dotted line at that asymptote. That's always a really good thing to show, yes, I know where that asymptote is. I know where the boundary, the leftmost boundary basically of the domain is. And so that's what the graph's going to look like. Okay, now what was it next? 7. 7 is going to be yet another graph. They didn't have, I would have preferred like more matching examples. They didn't have a lot of good ones here that I liked. So again, this is a little unrealistic. It would be more like, here's the graph. Find the equation. You'd have to recognize, okay, if it's going through 2, 0, it's going to be something that's shifted over by 1. And then, let's see, what's some other simple point? And I might actually give you this, like 4 comma 1. 4 comma 1. Well, I know it's shifted to the right, so that really came from 3 comma 1. Aha, the base must be 3. That would be the reasoning there. Okay, so now one more time, cheating with the computer here. How would you get this by hand, or how would you analyze this? Well, this is upside down. That's really important. And the asymptote is now a vertical asymptote. Well, it's always vertical, but it's going up instead of down. So that indicates the flip upside down. And then what about the shift? Well, it's it's shifted because it's not going through 1, 0. Okay. So we know you look for that 1, 0 anchor and you say, hey, it's not there. Oh, it's been raised up by 2 units. So you know it's upside down because it's starting high and going down low. And you know it's raised up by 2 units because you look for where that 1, 0 anchor would move to. It's like the sine and cosine anchor points. It's the same role. Another check would be if you have this equation for it, you say, okay, suppose I know that it goes through 4 comma 0. Does this go through 4 comma 0? Yeah, log base 2 of 4 is 2 because 4 is just 2 squared, and so 2 minus 2 is 0. Okay, so that would tell us that, for example, if I gave you this graph and said find an equation of like the form c or like a plus b log 2x, something like that, then you can find the equation. Just look for anchor points, understand flipping and shifting, and then double check with whatever points you can find. So 13, find the domain of the function. I don't think I would ask I think I decided not to ask something like that, so let's skip that. 19. Okay, well, write the equation in exponential form. This is the absolute basic connection. If log x equals y, then x equals, now this is log with no subscript, then x is 10 to the y. This says that y is the mystery exponent that I have to raise 10 to in order to get x, and then I just write that down. I say, okay, if I want to get x itself, I just go ahead and do that. I raise 10 to the y. That is a basic connection that you definitely need to have mastered. 23, write the equation in logarithmic form. 10 to the x equals 74. Okay. Well, again, it's the basic definition of logarithms. X is the mystery exponent that I have to raise 10 to. Again, it would be log base 10, but we often just write that without the 10, of 74. Pretty simple, I hope. 27. Evaluate the expression without using a calculator. Now, I wouldn't exactly have this kind of thing on our test, to be honest, because I decided to make it all calculator active. But it's still really good practice, because I could definitely do something like this with letters, for example, and say simplify. And you wouldn't be able to use the calculator. 10 to a log, and that's a log base 10, because I didn't put a subscript. Those always cancel out. And they just cancel it out, and you just get 45. That's it. That's all there is to it. And a more complicated way to say it is log 45 is the mystery number that I have to raise 10 to in order to get 45, and then I go ahead and do that. I actually raise 10 to that mystery number, and who knows what it is, but its role is that when I raise 10 to it, I get 45 back. Okay. And 31. That was 29. No, 29. 29, we've got in the other order and with a different base. But again, logs and exponentials cancel each other out. I take 6, I raise e to that, and I say, what number did I just raise e to? Because that's what ln says. Well, guess what? I didn't make it any mystery at all. It's just 6. 31, is that right? Yeah, 31. Log base 3 of 1/27. So we really want to make it as much like this problem as possible. Without a calculator, we have to, the only way we could do it is we can recognize that what's inside is of the form 3 to some power. Well, it is. It's 3 to the minus 3, because the minus gives the 1 over, and then 27 is 3 cubed. And now, just the basic properties that they cancel out gives you minus 3. Pretty simple. 39. Getting less simple. Here we're using rules of logs. Log 8, 6 minus log base 8 of 3 plus log, whoa, it didn't work, pay attention, plus log base 8 of 2. Okay, we have to remember how to combine these. Log base 8, because these individually you can't do without a calculator. This one you could do, but these you can't do without a calculator. These are not nice numbers, but combined it's going to be nice. because subtraction means division and addition means multiplication. So let's reorder it a little bit. We're really multiplying the 6 and the 2, and then we're dividing by 3. And so that's going to be just log base 8 of 4. Yep, log base 8 of 4. And now we just have to express 4 as a power of 8. Well, that's kind of weird. Is it a nice power of 8? Well, it's not an integer power of 8. But it is 2 squared. So that's 2 to the 1/3. Sorry, 8 to the 1/3. So bring it down to the sort of the common base and then square it. So if you take 8 to the 1/3, you get down to 2. And then you square it, you get 4. So just simplify that a little bit. Log base 8, use our rules of exponential. So that's really just saying 4, a very complicated way to write the number 4 is 8 to the 2/3. And now finally they can cancel out and you get 2/3. Okay, that's definitely a bit more complicated. But we have all the tools necessary to do that. 43, more rules of logs. Log of root x squared minus 1 over x squared plus 1. Now you have to either use the special rule that says log of root is equal to something, or you can just always realize that a root is just a power. So you can think of the root as a special rule, but it's probably better just to think of it as, hey, that's a 1/2 power. So you get 1/2 coming out, and then ln of what's inside. Okay, now that I can still expand that. That's the difference of the logs. Now remember, the operation moves and changes. The operation was division when it's inside. When it comes out of the expression, and it changes down the rungs of the hierarchy, down the ladder to minus, to a subtraction. Now there's not much more we could do with this. You could express this as a product and then even make it a little more complicated. But this is probably as good as you'd want to get. We've really used the fundamental rules here. And in particular, it's definitely not possible to say like it's ln of x squared minus ln1 and then ln x squared plus ln1. Remember, minus and plus inside here, there's nowhere down on the hierarchy that's really that they can go, and there's no rule for log of a difference or log of a sum. There's a rule for difference of logs, which is this guy, but not a log of a difference or log of a sum. And 51, we got similar kind of problem, but a little backwards. Log of x minus 2. Here the goal is to put it all together. And we haven't really focused yet. Your homework for after the test is going to be watching more video about solving these equations involving logs and things. That's where this starts to have a payoff of why would you put this together as one log? Well, logs are complicated. They're wonderful, but they are complicated, and fewer of them might be a better idea. Okay, so I could add those, but I'm going to wait a second because I need to do this subtraction, and first I need to deal with 1/2. So one of the things that's important is you always deal with any coefficients in front first. So I'm just going to take this, I'm just going to copy that, and I'm going to realize that that's really a root. I'm going to do exactly the opposite of the first step last time, and that's the log of a root. Now we just have a sum or difference of logs with nothing in front, and that's where I can use my basic rules. This is multiplication. Use big old square brackets here. That's the product, and then it's all divided by x squared plus 4. It's kind of magic. I mean, logs it's amazing that these properties hold. They're so incredibly useful. They're incredibly useful in history. If they seem weird, don't think, oh, they're weird because I don't really believe them. But you can think they're weird because they're really cool. They're powerful. They're not something that you'd necessarily expect would ever be possible to do. Okay, so that was 51. 53. Solve the equation. I thought I deleted these guys. Oh, okay. Well, let's just solve one of these guys, because this isn't too hard. Okay. This might be a little more complicated than what I would put on the test, but this is really not hard, because it's really just about using the basic rules of logs and exponentials. If it's just like what we had a few times ago on number, what was it? Taking a log equation and expressing it like this, basically, like number 19. Okay, so 1 minus x is just going to be 2 to the 4th. If 1 minus x is a number that the magic exponent with base 2 to get that number is 4, then 1 minus x must be 2 to the 4th. Okay, and so x is just going to be 1 minus 2 to the 4th, which is minus 15. Hey, wait, I thought you couldn't take the log of a negative number. Ah, but you're not. 1 minus minus 15 gives you 16. Log 2 of 16 is indeed 4. Okay, so that's a very simple example of solving equations with logs. And then one more, 81. Little applied problem with money. We love money. We got $12,000. Yeah, so P equals $12,000. R equals 10% or 0.10. And T equals 3 years. Okay. And so A, we've got the amount after the end of 3 years. We got semi-annual compounding. So we're going to take 12,000 times 1 plus, we're going to take that 0.1 and divide it in 2, and then 2 times 3, because we got 6 compounding periods. And then we're just going to evaluate that. Pretty easy. Okay, so 16,081. Not too shabby for just 3 years of investing. Okay, B, A equals 12,000. And then this is monthly. That's a more standard kind of thing. So here, every month you're getting less than 1%. Oh, that's too bad. But you're getting it 36 times. And so, okay, so it's a little bit more money. And we've observed that if all you want is sort of seat of the pants estimates, it hardly even matters what the compounding period is. And I usually just default to continuous because it's a simpler formula and it has E in it, which is so cool. But if you're the actual bank, that you can't get away with that. You know, people want those extra few dollars. Daily, ooh boy. And you know, it's a little disappointing. You're like, oh man, daily, that's cool. They're giving me money so often. Well, they're not giving me much extra money every day, and we don't get a lot more money. 16,198. Okay. I don't know. I would guess maybe a little bit less difference. And then continuously, of course, we have to go to a different formula. But a simple formula. E to the RT is just 0.10 times 3. And that is as good as you can get with this interest rate. And guess what? It's the same as daily to the nearest dollar. Okay. If we counted the cents, this defaults to 5 significant figures. If we counted the cents, I'm sure it would be a little different from daily, but not very different. And that's the motto, is that once you get to a really pretty high compounding rate, it doesn't matter. Just go to the E formula. Okay.